Hi, I'm Mehtaab, and today I'll be discussing approximate counting and sampling via local central limit theorems. And this is all joint work with Vishesh Jain, who's at Stanford, Perkins, who's at UIC, and Ashwin, who's at MIT. So we'll be concerned with algorithmic questions involving independent sets. And throughout the talk, G will be a graph which is simple, unweighted, and undirected on n vertices with maximum degree delta. And throughout this talk, we will think of delta as fixed and n as large. And there are many natural and well-studied algorithmic questions involving independent sets of a graph G. In particular, one can ask to exactly or approximately determine the independence number, e.g. the size of the largest independent set of G. One could also ask to exactly or approximately count the total number of independent sets of a graph G. And finally, the algorithmic question, which will be most closely related to what we're discussing today, is to determine exactly or approximately the total number of independent sets of a graph G of a given size K. And throughout the talk, we'll denote this quantity by Ik of G. So in particular, Ik of G is the total number of independent sets of size K in a graph G. And there are numerous results in this direction. So the exact problem turns out to be sharply hard, even restricted to line graphs of bipartite graphs. And this is a result of Valiant. However, for certain special classes of graph G, it turns out that there are good algorithms. So in particular, for line graphs of planar graphs on 2n vertices and taking K to be n, so this is equivalent to counting perfect matchings in planar graphs, there is a deterministic polynomial time algorithm due to Castellan from 1967. Furthermore, there are fully polynomial randomized approximation schemes known for all values of K in certain special cases. So in particular, for line graphs of bipartite graphs, there's a result of Jerem, Sinclair, and Vigoda from 2004, and more recent breakthrough work of Almadi, Anari, Sugar, and Vong regarding line graphs of planar graphs. And it's a major open problem whether there's an FPROS for all values of K for line graphs of general graphs. Throughout this talk, we'll be focused on a different setting on our where we take general graphs G, but have a restriction on the maximum degree delta. And it turns out that in this generality, there's no FPROS for Ik of G unless NP equals RP for K bigger than some alpha critical of delta. And this is a result of Davies and Perkins. And alpha critical of delta has this particular form. And for small values of delta, they're listed on the slide. Maybe one thing to note is that alpha critical of delta scales like E over E plus 1 times 1 over delta for large delta. So in particular, the greedy algorithm tells you that there's an independent set of size roughly n over delta, but one can't hope to count the number of independent sets of this size given the result of Davies and Perkins. And actually, you can't hope to count it even quite a bit below that, below the, let's say, the size you can construct greedily. And what we'll be considering is sort of, so one natural, so instead of just directly counting, one can sort of ask a very similar question regarding sampling a uniformly random independent set, or a closely related question, which is sampling fixed matching of nearly maximum size. So the first result in this direction is due to Jerem and Sinclair, who showed that one can sample up to 1 minus delta times the maximum matching size in time n to the 7 halves. For independent sets, there was a result of Bubbly and Dyer in 97, which shows that one can in nearly linear time sample an independent set of size at most n over 2 delta. So this is within a constant factor of optimal, but doesn't go all the way up to the critical threshold. There was also work of Ave and Lau, which gave a bound of n up to size n over delta plus the absolute value of the minimum eigenvalue. However, they get a runtime of k squared. So if k is linear, this is slower than the result of Bubbly and Dyer, but can be sharper depending on, the result can be sharper depending on the size of the minimum eigenvalue. Then there was results of Chen, Liu, and Vigoda, which in the matching case gave a running time of n to the 3 halves. There's a dagger there, which we'll explain. And then there was work of Davies and Perkins, which got up to the critical threshold, but the running time was expensive, so it was order n cubed. And one of our main results is to give a nearly linear time algorithm for sampling independent sets or independent sets either up to the critical threshold or matchings up to the maximum size in time that's O tilde of n for constant degree graphs. Furthermore, instead of simply asking the randomized question, one can instead ask, can one count the number of independent sets or matchings of fixed size deterministically? So in particular, can we deterministically approximate ik of g and mk of g up to 1 minus delta times the threshold? And here the threshold as before is n times alpha critical of delta in the general independent set case, and the matching number in the matching case. And results of Davies, Jensen, and Perkins based on cluster expansion gave a polynomial time algorithm for constant degree graphs up to the constant threshold, but within a multiplicative factor. So you take the threshold and divide it by 50, then there was an algorithm based on cluster expansion techniques which worked. And our main result, one of our main results, is to give a polynomial time algorithm which works all the way up to the critical threshold. So if you're 1 minus delta times the critical threshold, then we give an n to the O little delta capital delta algorithm, n to the some polynomial depending on this, how close you are to the threshold and the maximum degree. And our results sort of rely on relating independent sets of a fixed size to the hardcore model. So let me define the hardcore model precisely. The hardcore model is a distribution on the independent sets of a graph G. So in order to do this, first let's define the independence polynomial of a graph G. So Ig of lambda is the sum from k equals 0 to the size of the maximum independence set, or the independence number, of ik of g times lambda to the k. And the natural hardcore model is to sample an independence at I proportional to lambda to the I. And to normalize, one needs to divide by this normalizing constant, which turns out to be exactly Ig of lambda. So in particular, more precisely, the hardcore model samples a fixed independence at I with probability lambda to the size of I over Ig of lambda. And using terms of statistical physics, Ig of lambda is the partition function associated to the hardcore model of G. And it turns out that we have very precise understanding of when one can approximate Ig of lambda. So in particular, there's a famous result of Weitz that there's an FP-toss for computing Ig of lambda all the way up to lambda, where lambda to 1 minus delta times some critical value, lambda critical of delta. And lambda critical of delta is written on the slide. For large delta, it's roughly E over delta. One of the reasons this result is so remarkable is that there's other breakthrough work of Sly and Sly-Son and Galanis, Stefankovich, and Vigoda, which shows that this threshold is really sharp. In particular, there's no FP Ross unless NP equals RP for Ig of lambda once lambda is bigger than this critical threshold. So somehow this is a very precise computational, it's below this threshold, it's computationally feasible, and above it's hard, assuming well-known complexity conjectures. And our alpha critical of delta actually comes from this lambda critical of delta. In particular, alpha critical of delta is the expected density of an independent set drawn from the hardcore model on the complete graph at this fugacity. And so one can use this fact to prove, to sort of bootstrap, and this is what Davies and Perkins do, one can bootstrap the previous hardness to hardness for sampling, to counting the number of independent sets of a fixed size. However, this also has an algorithmic, one could turn this on its head and use this for algorithms. In particular, this means for any graph G with maximum degree delta and K, which is below this threshold, there exists a lambda below the corresponding lambda critical of delta, such that the expected size of the independent set drawn from the hardcore model at that lambda is close to the size you want. So in particular, mu of lambda, which is the expected size of the independent set drawn at fugacity lambda for graph G, is close to the K you want. So it's within, let's say, a half. Given this, we don't actually know that our independent set drawn from this hardcore model needs to be, its mean might be close, but you might never actually hit that value. And this motivates sort of proving a local central limit theorem, which would say, okay, not only is the mean close, but you hit every value. You have not only do you have a central limit theorem, but you have a local limit theorem. So every value takes on approximately what you would expect if the distribution really looked like a Gaussian at every point. So in this form, what it would have is the probability that your independent set is of size L would be this function written. And the way to interpret this function is this is, let's say you have a Gaussian of mean mu of lambda and variance sigma of lambda. This is the area between L to the minus 1/2 and L to the L plus 1/2 under that Gaussian distribution. And you're very close. In particular, you're within little o of 1 over sigma of lambda. So somehow you're very, very close to the Gaussian approximation. And the main probabilistic result of our paper is to show that the size of the independent set, given that lambda is not too small and below the critical threshold, it does satisfy an LCLT. And using this and the proof of the LCLT, one can establish the algorithmic consequences mentioned earlier. So the key step in our proof of the local central limit theorem is a sort of decoupling argument. So we proceed via Fourier analysis, and we need to somehow extract independent random variables from this hardcore model, which naively has there's no obvious independence. So the simple fact we use is that given a graph G of maximum degree delta, there exists a set of vertices S of linear size, so O theta delta of n, such that for every vertex V and S, V and the neighborhood of V are disjoint for all vertices V and S. So we decompose our whole graph G into a set T, union V, V and its neighborhood for V and S. Then what we do is we denote nu of lambda to be the distribution of independent sets on T induced by the hardcore model. So in particular, sample an independent set on the whole graph and then just restrict it to T. And using this, one can then give a decomposition for the hardcore measure that has many independent parts. So what you do is you first sample an independent set on the whole graph, then restrict it to T, and then resample. So given this restriction of your whole independent set onto T, one can then resample the vertex and every vertex and its neighbor in S independently. And notice by this condition of being separated, we have that given the independent set on T, the independent set on the vertex and V and the neighborhood of V for every vertex V and S turn out to be independent. So this gives us a form of conditional independence. In particular, we can write the size of the independent set I as the size of I equals the size of J, where J is the size of the independent set on our set T, plus this plus a set of random variables which are independent given the independent set on T. And using this plus elementary considerations, one can sort of bound the size of the Fourier coefficient. So in particular, we look at e to the it times the size of I, and we want to show that this is small. So what one can do is, just by the triangle inequality, this is bounded by the expectation under the hardcore measure of e to the it times the size of I, given any realization of the independent set on T, which we're calling J. Then using the independence of x1 through xs given J, we can write this as a product. And then elementary computation, you can bound this by x of minus lambda t squared n with hidden constants depending on delta, depending on how close we are to the critical threshold and the maximum degree delta. Then our proof of a zero-free region relies on sort of using Fourier inversion. So first we'll need a fact about the variance and that it's order lambda times n. And this follows from a computation using the zero-free region for the independence polynomial established by Peters and Rex. Then we write the probability of lambda of x equaling x. So that the sampled independent, so we first normalize the size of the independent set I to be I minus its mean mu of h divided by sigma of h. And we want to show that this random variable is close to a Gaussian or a discrete Gaussian in some appropriate sense. So what one can do is apply Fourier inversion on the lattice. And then we want that, so knowing that the probability I equals k is the same as knowing that this random variable x equals k minus mu of h over sigma of h. Using Fourier inversion, this has some, this can be written as a Fourier integral. And we split this integral into two parts based on the size of the phase t. So if t turns out to be larger than square root of log of 1 over delta, then by our previous analysis, this turns out to be smaller. The contribution from that part of the integral turns out to be smaller than epsilon to the 100 divided by sigma of h. And the second part, we have to concern ourselves with small phases. And so one of the key points is that one can control this using a zero-free region. So we need to control the normalized contribution coming from small phases. And here for what we use is a general result concerning zero-free regions regarding the independence polynomial of a fixed degree graph established by Peters and Rex, and a general theorem of Michelin-Sahastra-Budde, which turns zero-free regions of probability generating functions to central limit theorems. So given this, we know that x, instead of just so we need to establish a local central limit theorem. So in order to establish a local central limit theorem, I'm going to need a central limit theorem to come from somewhere. And this zero-free region plus this general result of Michelin-Sahastra-Budde gives you that central limit theorem. And given that you're close to given that you're close to a normal distribution in some distributional sense written at the bottom of the slide, one can use integration by parts to show that the corresponding Fourier coefficients are also close. And given this bound and integrating, one can then prove that you have a local central limit theorem. To get our fully polynomial time approximation schemes for ik of g, we use polynomial interpolation plus the zero-free region established by Peters and Rex, plus the fact that Barvanak's polynomial interpolation, which generally runs in quasi-polynomial time, this can be run in polynomial time for bounded in this particular setting due to a result of Patel and Rex. And here, the key point is that this Fourier coefficient e to the it of x can be written basically as the product of evaluating ig of lambda at two different values. And given this, one can show that some part of the integral is very small just by this decoupling argument. And for the remaining part of the integral, one simply computes it via Riemann integration and approximating each term using that's the ratio of these two values of the independence polynomial plus Barvanak's polynomial interpolation scheme. To get our sampling algorithms by the LCLT, we know that choosing an appropriate value of lambda for our size k, we can make it so that the probability that when we sample from the hardcore model that we get our desired size k is at least probability 1 over square root of n. Then using results regarding mixing of Glauber dynamics established by Chen, Liu, and Vigoda, plus rejection sampling, one can obtain an algorithm which gives a uniformly random independent set of a given size in time n to the 3/2. To give a linear time sampling algorithm, we instead need to open up the proof of the LCLT. And using this, one can establish a sampler which gives access to the distribution of the hardcore model conditional on being some fixed residue modulo a given integer of scale square root of n. So this allows you to, instead of having rejection probability 1 over square root of n, have rejection probability, have acceptance probability, which is order one. And this allows you to obtain a nearly linear time sampler. And the sampler really comes from sort of inverting the proof of the local central limit theorem. And with that, I will conclude my talk.